the last lecture I said that I am going to derive Mott's expression for the t to the power 1/4 law. For doing that, what we need to look at is the following. That is, we have to approximate delta E, which is actually the energy range accessible in the volume 4/3 pi r cubed, where r is the range of hop. Well, we know the definition of density of states. I have already said that before. So, if n of E is the density of states, it means that n of E is the number of states per unit energy around E per unit volume. So, that means that if I have to see a energy difference of delta E over a range of R, then it should go as, it is approximate. So, it is just a order of heuristic one. So, it should go as 1 upon volume, which is 4/3 pi r cubed, multiplied by the density of states n at E. So, once we have this expression for delta E of R, then we know that P of R we can write as equal to P of R naught exponential minus W of R. So, what is W of R? W of R is equal to minus 2 alpha R. Actually, it is plus 2 alpha R because I have taken the minus sign on top, plus 3 by 4 pi r cubed n of E times kBT. Well, the most probable hop, if I want to look at, then I should be able to minimize W of R. So, the distance R naught over which the hop occurs corresponds to minimum value of WR. Minimum of WR. So, if I differentiate it, I have dW of R by dr is equal to 2 alpha plus 9 divided by 4 pi r to the power 4 n of E into kBT. So, from this I get an expression for this is equal to 0 for R naught, which is the minimum. So, I can get an expression for R naught, and the expression for R naught is simple. We can write it down as 9 upon 8 pi alpha times n of E times kBT raised to the power 1/4. Now, what we can do, if we substitute R naught for R in W of R, what we obtain is a form of the type W of R naught going as some T naught by T to the power 1/4. This is quite simple to do it. I would encourage you to try, and where T naught has this form 8 alpha cubed divided by 9 pi n of E into kb. Okay, so The reason why you will get T naught to the power 1/4 is simply because you have r to the power 4 here, and so if you do the algebra you will get it. So if W of r naught goes as T naught by T to the power 1/4, then this implies that the conductivity shows the T to the power 1/4 law. The problem with this expression is the following, that is, T to the power 1/4 law, it is not very sensitive. That is, whether the sensitivity of the conductivity expression sigma T to the power alpha in T to the power alpha is very poor. The experimental data that you get, you can fit it to alpha equal to 1/3 or 1 or even 1/2 sometimes. So while T to the power 1/4 law is very nice to look at, but it is not really a very useful thing. But anyway, I will not go beyond this in discussing randomness and disordered solids. In the next part of the lecture, what I will be talking about is optical properties of semiconductors. So what we know is that, in any given an atom or a molecule, you have a whole bunch of energy levels. Okay, so you can have a bunch of energy levels, and some of them are occupied. Let us say, the lower two levels are occupied. Then if you want to find out the gap, at least in the non-interacting picture, between the highest occupied molecular orbital and the lowest unoccupied molecular orbital, what you do is you do an experiment which is an optical absorption experiment. You do an optical absorption experiment. So you will excite from here to there, and you say that h nu, the energy for excitation, is going to be equal to the gap between E lumo minus E homo. In some sense, this is not very different from a semiconducting solid. In a semiconducting solid, we have a filled valence band and an empty conduction band, at least at absolute 0 Kelvin, and empty conduction band at 0 Kelvin. So you would expect that you will have an absorption. This is the conduction band, and this is the valence band. The valence band is filled, conduction band is empty. So you assume that there is going to be an absorption from here to there. So you have when you have an absorption, what results is actually a hole and you put the particle electron there. So, and this is the minimum energy for absorption. Well, let me use h cross, it is more convenient. H cross omega, this is the minimum, so that E of G, the band gap, is equal to h cross omega minimum. And this should technically, at least looking at this, it should correspond to omega minimum corresponds to absorption edge. Well, is that true always? We have to look at the following, that is, whenever we are talking about a solid or a crystal, in crystals we have two conservation laws. For absorption process. One is energy should be conserved. So what it means is that H cross omega is equal to E final minus E initial. And 2, momentum should also be conserved. And this second one should be conserved to within a reciprocal lattice translation vector, RLTV. So we can have two kinds of semiconductors. One is what are called the direct band gap semiconductors. These are actually characterized by the, if I plot the dispersion curves for the valence band and the conduction band, they will look like this. So this will be the valence band and this will be the conduction band. And what you will see is that the maxima in the valence band is at the same k point, energy, and this is k, as the minima in the conduction band. So what it means is that the momentum change delta k equal to final momentum minus initial momentum. Let me put H cross. This is equal to 0. We also know that the momentum of the photon is almost zilch. The photon momentum can be ignored for small photon energies like a few electron volts. You can find out what it should be by knowing that the dispersion relationship is the following, that is E of photon is equal to H cross times omega k, or omega k equal to H cross times C of k, right, because what you have is d omega by dk is equal to the group velocity, which is the velocity of light. So you can calculate for a few electron volts what the momentum is, it's zilch. So the transition from maximum in the valence band to the minimum in the conduction band is allowed both by energy conservation and momentum conservation rules. Energy and momentum conservation rules. So, what you will see is if I plot energy absorbance versus energy of the photon, which is h cross omega, let me call it E photon, then what you will see is this is Eg. Eg is the band gap, and absorbance is determined by transition by dipole transition matrix, by dipole transition transition dipole matrix element. And joint density of states for the valence band and conduction band at the energy E photon. Okay, so that is why you have this usually goes as some kind of a square root E dependence. So, and these materials are like I already said, like germanium, gallium arsenide, indium antimonide. These are some of the materials which have got direct band gap, and the absorbance in these cases is pretty large. So, that is the reason why if you have these materials and you make a solar cell using these materials, the efficiency of the solar cells will be very high. Unfortunately, something like silicon is an indirect band gap material. So, although it is easy to work with silicon technology is very well established, but even then the efficiency involving silicon will be lower because it is an indirect band gap material. So, what is meant by indirect band gap material? In the indirect band gap material, what we have is the following. That is, we have this is the conduction band, and so let me call this K, and this is the valence band, this is energy. So, the band gap in this case is actually for all thermal experiments involving thermal experiments, the band gap Eg is not at the same point, okay, is not at the same point in K space. Or actually it is not the band gap. What I am saying is that EVB max and ECB min are not at the same point in K space. So, how can this happen? So, what happens is the following, that is, the momentum is not conserved. When I say momentum, it is the crystal momentum, is not conserved in this transition. So that means I can say in red that this is not a load. Because the energy conservation can be satisfied but momentum conservation cannot be satisfied. So how does the system actually allow such a transition? So what happens is the following: the momentum conservation, the momentum balance is obtained by creating or annihilating a phonon. A phonon of momentum q equal to k, this is conduction band minimum, minus k valence band maximum. So what we mean by that is the following, that is phonons are nothing but lattice vibrations, and lattice vibrations in a solid will also be, the normal modes correspond to a modulated displacement of all the atoms in the crystal in a fashion which is very similar to the overlap of orbitals that we were talking about in constructing the molecular orbitals in a periodic system. So except that there we were talking about orbitals at every side, and here we are talking about displacement at every side, and these displacements can be analyzed in terms of the wave vectors, just as the molecular orbitals were labeled by wave vectors, and this coordinate that you get, which is the u of q, will be the normal modes. So if I am looking just at a chain, then the normal modes are nothing but u of q is equal to sigma over n e to the iq dot rn u of r minus rn, where u is the displacement. At the site Rn. So if there is time, we will go into this one a little bit more in detail later in the course. So what happens is that now the energy conservation rule will be as follows: the photon energy h cross omega must be equal to E conduction band minimum minus E valence band maximum plus minus h cross omega q, where omega q is the normal mode frequency of the lattice. And the momentum conservation will now be that k conduction band minimum minus k valence band maximum plus minus q is equal to 0. Okay, and what we have is that when we excite a normal mode, or when we create a phonon, when we excite a normal mode, which is the same thing as creating a phonon, just a matter of language, then h cross omega is equal to, let me call it Eg plus h cross omega q. Whereas when we are de-exciting in normal mode, then when we de-excite a normal mode, which is the same thing as annihilate a phonon, then h cross omega is equal to Eg minus h cross omega q. So, what we actually see is the following, that is if we go back to the old picture, then what happens is you create a phonon of this momentum. This is nothing but h cross q. Okay, so you create or annihilate a phonon of that momentum, then you will be able to make the transition. So it's basically what one is looking at is our vibronic transitions. So these are called vibronic transitions. Because it involves both electronic and vibrational transition. Although is what takes place. In indirect band gap materials. Here we can also notice one more thing, that is at low temperatures number of phonons in the system is small. Or in other words, most of the vibrational modes are in the ground state with rather low momentum, okay, because these are acoustic modes. In acoustic modes, omega goes as CQ, and so C is the sound velocity. And what you will find is that at low temperatures, the only phonons that are available are those which have small wave vectors and not the large wave vectors. So in this case, the dominant vibronic process involves creation of phonons. So creation of phonons means that you have to spend more photon energy in order to excite the vibrational state. So that's what happens at low temperatures. At high temperatures, both are equally probable, which is actually that you can either create or annihilate a phonon, and the way the spectrum looks like is the following. The spectrum looks like alpha absorption versus h cross omega goes as so if I am looking at the two temperatures T1 and T2, then what we are saying is that T1 is greater than T2 because you are able to annihilate phonons, and which means that you are taking away lattice vibrational energy and giving it to the electron, in which case the amount of photon energy that is required for making the transition is lower, and that is why you have a lower threshold. But on the other hand, at low temperatures, which is at T2, you will have a higher threshold. So this is what happens to alpha absorption, and if you plot alpha to the power half versus the photon energy, you will find a knee curve. Okay, so it will go like this. In this, if you extrapolate the knee, okay, the upper straight line down, so then what you will see is that this is 2h cross omega q, and you will be able to get from this the actual band gap in the system after correcting for the phonon energies. So, we have shown the cases where we will have semiconductors. There are two cases, the direct and the indirect band gap materials, and in indirect band gap materials the intensity of absorption alpha absorption is small, because it involves both an electronic process and a vibrational excitation and an electronic excitation as a product of both the transition matrix elements. And the kind of materials that you have which exhibit this are the most famous. Silicon is an indirect band gap material. So, in metals what happens? Okay. So, if I am looking at metals, what I have is the following, that is I have energy versus K. So, it goes the dispersion goes like that, and the states are occupied up to some Fermi energy. Now, if you want to make an intraband transition, what you require are phonon assistance. So, usually for large momentum transfer, change between initial and final states, I will show you an example. That is, if I have a state here, say there, and then I want to excite it to this state, the momentum transfer h cross q is large. So, you require an interband this thing, a participation of a phonon. But if you are just trying to excite from here to here, say for example from here to here, just across the Fermi level at the same just across the Fermi surface, then we do not need the participation of phonons. So, we need assistance of phonon assistance, but for transitions just across the Fermi surface, no phonon needs to be created or destroyed. Actually, you see that the energy change delta E for intraband transition is very small. Is continuously varying actually. From 0 to the band maximum minus the Fermi energy. Okay. What you will see is that light of all wavelengths will be absorbed, light of all In particular, if you are looking at microwaves, microwaves will be absorbed by these metals, and that is the reason why you never put a metallic vessel containing food for heating up in a microwave oven. So, because all the microwave will be absorbed by the metal and you will not see, the food won't get heated, although nothing dangerous happens unless the metal has very sharp edges, then it will start sparking. Okay, so this is all that I wanted to say about optical properties of semiconductors, mainly the direct band gap and indirect band gap transitions. In the next lecture, what I will talk about is the excitonic states in semiconductors and how one observes them, and what are the types of excitons. There are two different kinds of excitons, which are basically the Frenkel excitons and the Mott-Wannier excitons. We will show you what the difference between these two are, and we will meet again in the next lecture. Thank you very much.